Greetings and welcome to a quick lecture on linear equations in one variable. I'm your presenter, Lynn Mann. We have three primary objectives for this lecture. The first is to learn some vocabulary and concepts so we can speak the same language. Second, we're going to solve linear equations in one variable using some standard steps to follow. And the third is we're going to solve formulas for a particular variable. Now we won't get a numeric answer. We're actually going to solve for one variable and have the rest of the formula on the other side of the equation. Our first terminology, vocabulary word here is equation. An equation you've probably run into many a times in your past. It is a statement that two mathematical expressions are equal. For example, 7 minus 5, that's on one side of the equal marker, and 2 is on the other side of the equal marker. And an equation is where those two sides are equal. An equation in one variable is the same type of statement, but there's a variable running around. There's a letter running around either on just one side of the equation or on both sides of the equation. So for example, 2x minus 3 equals 7 is an equation with one variable. The domain of the variable for an equation is the set of all real numbers for which both sides of the equation are defined, which means we're not setting off any, alarm bells like if we have a fraction, we don't want the denominator to be 0. If we have a square root, then we don't want that square root to contain a negative value because then we're not in the real numbers. We're in another set of numbers. So we want to stay in the real numbers. So the domain is all the values for x that make that equation, number one, true, and to fit within the real numbers. Let's take a look at an example to find the domain of a variable. Keep in mind that we're looking for all x values that make our equation valid in the real numbers. And the only problematic times that we really get is when we have fractions and the variable is down in the denominator. I don't even care if it's in the numerator, but if it's in the denominator, that can cause problems, as well as if an x is inside a square root in the real numbers, that causes problems for certain values of x. So let's look at this equation and find a solution to our domain. On the left-hand side, there's no issues. There's not even an x over there, so if you threw x equals 5, it wouldn't matter because there's no x on the left-hand side. So all values of x are defined, meaning we stay in the real numbers. The problem comes with the right-hand side because we have our x in the denominator, and we don't want denominators to be 0. So we need to find the value of x that forces that denominator to be 0. Once we find that value, we just throw it out and say, hey, we're not allowed to use that, but everything else is good. When x equals 1, we get 1 minus 1 in the denominator. That equals 0. So the problem value is when x equals 1. And therefore, our domain is everything but when x equals 1. One way of simply writing it, we just say, hey, here's our equation, 2 equals 5 over x minus 1, as long as x does not equal 1. Let's run through another example. This time we have x minus 2 equals the square root of x, and we're looking for all the values of x where we stay in the real numbers. Now looking at the left-hand side, we have no issues. X can be anything. Let's just throw negative 10 in there. Negative 10 minus 2 is negative 12. That's perfectly okay. Let's throw a positive value in there. Let's go with 10 because it's simple. 10 minus 2 is 8. That's still a real number, so we're good there. And we can even throw 0 in there. 0 minus 2 is negative 2. That's still a real number. On the left, no problems at all. X can be anything it wants to be, and that left-hand side is still going to be a real number. Aha! But the right-hand side is a square root, and remember, we want to stay in the real numbers. When we take a square root of a negative number, we are no longer in the real numbers. What values of x make that value inside the radical negative? Well, all negative numbers. So x equals -1, yeah, that's negative, problematic. X equals -10, yeah, problematic. X equals 0, oh, hey, that's okay. Square root of 0 is 0, so that's a real number. X equals 1, square root of 1 is 1, no problem. X equals 2, that's 1.717 something, right? It's still a real number. Might be irrational, but it's still a real number. So it looks like we have problems when x's are negative, but as long as x is 0 or more, 0 or greater, then we're good. So the right-hand side is defined when x is 0 or greater. We limit our x's to be those x's such that x is greater than or equal to 0. That line going up and down between the x's is read as such that. X such that x's are greater than or equal to 0. One way of writing it. Another way of writing it is interval notation. Since we're including the 0, we'll throw a bracket next to that 0, and it goes to positive infinity. We never include infinity because it is not a number, it's a concept. So next to any infinity, whether it's negative infinity or positive infinity, you always have the parenthesis marker. If we didn't include 0, we would use parenthesis next to 0. But this case, we are including it. Let's run through one more example of finding the domain. Now, if you remember, there's a couple of problematic situations. One, if we have a fraction. Two, if we have a square root. In this equation, we don't have any problematic situations. We don't have any fractions, we don't have any square root, and therefore, on the left-hand side, x can be anything, and we stay in the real numbers, and then there is no x on the right-hand side, so again, we don't have to worry about x being any value in particular. So both sides, all values of x are defined. We can write it in set notation as in x such that x is a real number, or in interval notation where we say parenthesis, negative infinity, all the way up to positive infinity, and parenthesis. Now you've probably seen these steps before. You've probably have solved similar equation in the past, but I'm going to refresh your memory on the steps, the procedure on how to solve linear equations with one variable. The first thing you want to do is take a look and see if you have any fractions, because I'll agree with you. Fractions are a bear to work with. So if we can get rid of those fractions during our procedure, that makes our life less complicated. To do that, you want to multiply by the LCD of all the denominators. You want to look at all your denominators and see what value they can each multiply into, and then multiply each term by that LCD. Once you do that, simplify. So you'll have a step where you're going to simplify those fractions, and I'll show you an example. Then you're going to isolate the variable term, meaning you're going to try and get the variable all by itself on one side and then the constants on the other side. If you have to, combine terms to be able to do that. At this point, isolate the variable, meaning generally you will have the variable has a coefficient, a number in front of it. Step 3 and step 5 are different. Step 3 is you're isolating the variable term, meaning the value in front of the x and the x combined is going to be on one side of the equation and the constants on the other, versus step 5 is you're actually going to solve for your variable. You're going to get the variable all by itself. And then ultimately in step 6, you want to check to see if your solution is correct. If maybe you did your math incorrect as we go along, then that's going to cause a problem with your solution. Here, we're primarily checking to make sure that our math was correct through steps 1 through 5. Let's run through a problem from start to finish. And yes, this problem does have fractions, so we are going to want to eliminate fractions. You don't have to. You can leave them as they are, but I encourage you to eliminate fractions because it just makes the process a lot easier if you're not dragging around fractions. First thing I want to do is I want to look to see what the LCD is for my denominators. I have a denominator of 3, 3, and 2, and therefore my LCD of 3, 3, and 2 is going to be a 6. A 3 can look like a 6 if I multiply it by a 2, and a 2 can look like a 6 if I multiply it by a 3. Now I'm going to multiply each of the fractions, each of the terms, by 6. So 6 times 1/3 x minus 6 times 2/3. That equals 6 times 1/2 times 1 minus 3x. Multiplying that 6 through, I get 6 over 3x minus 12 over 3 equals 6 over 2 times 1 minus 3x. Now at this point, we haven't eliminated the fractions until we hit step 2. Step 2 is simplify. So I'm going to go ahead and simplify these fractions, and I get 2x minus 4 equals 3 times 1 minus 3x. And at this point, I'm going to simplify it a little bit further by distributing that 3 into the 1 minus 3x. So I get 2x minus 4 equals 3 minus 9x. Now our next step, number 3, is to isolate the variable term, meaning get the term with all the x's on one side and everything else on the other side. So first thing, I have a 2x minus 4. I'm going to go ahead and move this 4 over to the other side by adding 4. So I get 2x minus 4 and a plus 4 cancels out. 3 minus x, 9x plus 4. And I'm going to move that negative 9x over to the left-hand side by adding. So let me add 9x to each side. I get 2x plus 9x equals 3 plus 4. Okay, at this point, we've hit step 4. Now you may do this kind of combining steps, combining 3 and 4, that's fine. I'm just laying out each step as it is just for this example. In future examples, I'll combine steps because it's easier to do it on the fly. 2x plus 9x is 11x, and 3 plus 4 equals 7. Now on to step 5. We have the final step in actually finding a solution is to isolate the variable, meaning solve for x. Because 11 is multiplying by x, I'm going to divide it, and that will get rid of it. But what I do to one side, I have to do to the other side because math likes balance. So I get a possible solution of x equals 7/11. Now I say possible solution because step 6 says we really should check to see if this value is indeed the solution. So let's go ahead and say x equals 7/11 and check to see if that indeed is our value. 1/3 times 7/11 minus 2/3, does that equal 1/2, let me throw that 3 in there, 3 times 7/11. I'm going to work on the left-hand side and then I'll jump over to the right-hand side. And if I get a value on the left that equals the value on the right, then I know my solution is good. 1 times 7 is 7. 3 times 11 is 33. Minus 2/3, but I need that to have the same denominator. So that's going to be 22 over 33 by multiplying both numerator and denominator by 11. 7 minus 22 is a negative 15 over 33. Now, if I get a negative 15 over 33 on the right, then my answer, my solution is good. 1/2, 1 minus 21 over 11. I can change this over to, what do I want to say, 11 over 11. So I got 11 over 11. That's still a 1. 11 minus 21 is 10. 10 over negative 10 over 11. That's going to be negative 10 over 22, which I can divide both of those by 2. I get negative 5 over 11. And if I divide the other side by 3, I get negative 5 over 11. And because both sides equal one another, my solution is good. All right, I'm going to run through solving for this linear equation, and I'm not going to do it formally by saying step 1, step 2, step 3. I'm just going to go through it as I would naturally. Because I have kind of parentheses within parentheses, I want to kind of start from the beginning parentheses, the most inward parenthesis, get rid of those, and work my way out. So the first thing I want to do is look at this parenthesis on the inside, see if I can simplify it a little bit. So I'm going to distribute this negative 2 both to the x and to the negative 2. 6x minus 3x minus 2x, and a negative times a negative is a positive 4. And that equals 11. Now anything in those brackets I want to simplify. So 3x and 2x, negative 2x, 6x minus bracket is a 1x plus 4. That's pretty simplified, equals 11. Now I can't just drop those brackets. I have this negative out front, and I'm going to have to distribute that throughout those brackets. Instead of having an implied value there, you can force it to be a 1 there, so it's a negative 1. That's if you want to. So now I have 6x. Multiplying a negative 1 to a 1x is a negative 1x, and a negative to a positive is a negative 4 equals 11. I'm going to combine like terms. So I have a 6x minus 1x is a 5x minus 4 equals 11. Again, isolating the variable term, I want to get rid of this 4, and because it's subtraction, I'll add which is the opposite operation. But I can't just do it to the left-hand side of the equation. I have to do it to the right-hand side of the equation as well. I get 5x equals 15. Last but not least, isolate the variable, which means solve for the variable. It's multiplying by 5, so if I divide by 5 to both sides, I get x equals 3 is a possible solution. But I want to double check this solution to make sure that it is correct. So I'm going to say my possible solution is x equals 3. And I'm just going to double check that. Yes, x equals 3. Wherever I see an x, I'm going to plug in this value of 3 and see if indeed I get on the left-hand side equaling the same thing as the right-hand side. Good news is nothing to do on the right-hand side, so I want to see if the left-hand side indeed equals 11. 6 times 3 minus 3 times 3 minus 2 times 3 minus 2 Does that indeed equal 11? 3 minus 2 is 1. Now I can do both of the multiplication of 3 times 3 and the 2 times 1 inside that parenthesis. 6 times 3 minus 3 times 3 is 9. 2 times 1 is 2. Again, staying within those brackets, following my order of operation. 9 minus 2 is 7. So I have 6 times 3 minus 7. 6 times 3 is 18. Minus 7. And indeed, 18 minus 7 is 11. And 11 equals 11. So yes, my solution of x minus 3 is good. On occasion, you might run into a linear equation that just doesn't make sense. You get the answer of something like 8 equals 3. Well, 8 doesn't equal 3. Or maybe you have negative 5 equals 10. Well, negative 5 doesn't equal 10. That's a situation where it's inconsistent. It's a linear equation that's inconsistent. So let's take a look at something at how this can happen. Starting with the inner parentheses, I'm going to distribute this 2. So I get 5x minus 3x plus 2x minus 2, and that equals 1. I'm going to combine what's inside those brackets. 5x minus 5x minus 2 equals 1. Next, I'm going to go ahead and distribute that negative through. If you need to see it, put a 1 in front and distribute a negative 1. I'm going to go ahead and just do the negative. 5x minus 5x, negative times a negative is a positive 2. And it turns out 5x minus 5x is 0, and I get an answer of 2 equals 1. Now, I don't know about you, in the decimal system, 2 never equals 1, and therefore it's inconsistent. There's just not an answer. There's no answer. So you can say it is the empty set, which is a circle with a line through it. You can use the set notation, which is just 2 brackets with nothing inside it, not even the empty set. Therefore, this linear equation just does not have a solution. Let's do one more situation you might run into, and that's when your end result is something like negative 3 equals negative 3, or 21 equals 21. Well, negative 3 does equal negative 3, and 21 does equal 21. And this is a situation, what is called the identity, linear equation identity. So let me run through this problem really quickly and solve. 1 minus 5y plus 2y plus 4. I'm going to simplify each side and see what I get. I get negative 3y plus 15 on the left, and I get negative 3y plus 15 on the right. At this point, you can stop because the left-hand side equals exactly the right-hand side. But I'm going to continue it one more step. I'm going to move the 3y from one side to the next, so you can see that 15 equals 15. In this case, 15 always equals 15, and therefore it's not dependent on the value of y. In fact, you can put any real number in for y, and you will get this true statement out, or a true statement out. So the answer, y, such that y is a real number. Any real number will make this solution true. It's the identity. In essence, there are 3 types of linear equations. The 3 types are: 1, we have the identity, meaning whatever value you are permitted to put in the domain is a valid answer. Second is when we have at least one value that's good, like x equals 3. The last type is that it's inconsistent. There is no value of x that you can put in that satisfies the equation to be equal on each side. And therefore, the empty set is the solution. Now, I know many students don't like word problems, aka application problems, but the world doesn't revolve around you given an equation like we saw before, 5x minus 3x, da 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 da. The world revolves around situations, and you will decipher the situation and what you need and turn it into the math for which you need to solve. So here we have a word problem. Introduction to this section described a television show in which bungee cord with a 140% to 150% elongation is used for contestants bungee jumping off of a bridge that is 120 feet above the water. The show producer wants to make sure that the jumper does not get closer than 10 feet to the water. How long can the bungee cord be given that the contestant will never be more than 7 feet tall? When dealing with application problems, if I can make a drawing of it, I find it very useful to kind of keep everything in my head straight. So I'm going to go ahead and draw an image of this situation. I will preface this, I am a horrible drawer. I can barely do a stick figure, so it's just really for me to keep ideas straight. First thing, we have a bridge. I'm just going to say that's what my bridge looks like. And we're going to have a bungee cord hanging off of that. And this bungee cord, from the point that it's just kind of hanging down, it can extend. So this is 150% of its length. It can elongate. And then on top of that, we have up to a 7-foot person. And just to keep everything safe, we need to keep this person 10 feet above the actual water. Now, I don't know how long this bungee cord is. I don't know the length of that bungee cord. So I'm going to go ahead and call it X feet long. I do know that this section is 150% of X, and because we don't really do math on percents, I'm going to change that to a decimal. So that is 1.5 X. Okay. So the whole entire length is 120 feet. The bridge sits 120 feet above the water. So I think I have everything I need to solve this puzzle, right? I know my bungee length is X. I know the extension is 1.5X. And I know the person is 7 feet, and I know above the water is 10 feet, and that better not extend more than 120. So step 2, let's go ahead and, since we don't know what length of cord we need, I'm going to go ahead and say X is the length of the bungee cord. Okay. And then I know for step 3, I know that the length of the cord plus 150% of the cord is going to be the maximum length that I can have of the bungee cord, right? The full length of the cord and then the 150% elongation. So that will be 2.5x. That's the maximum stretch that we want. Now, we have the extended cord length plus the person's body length plus a 10-foot buffer must equal the height of the bridge. Because if we go longer than the height of the bridge, we're in trouble. So let's fill all these in. The extended chord length is 2.5x. The body length, remember, is 7 feet, plus the 10 feet buffer can't be more than 120 feet. I can simplify this a little bit, so let's go with 2.5x plus 7 plus 10 equals 120. I'm going to simplify a little bit. And then ultimately solve for my x using all of the rules that I know. So plus 17, to get rid of a plus 17, I'm going to subtract 17 from both sides. I get 2.5x equals 103, right? 120 minus 17 is 103. I'm going to divide each side by 2.5. You can break out a calculator if you want. And we get, let's see, breaking out my calculator, 103 divided by 2.5, I get 41.2. And this is in feet. That means my maximum length of bungee can't be more than 41.2 feet. Now just to double check, let me go ahead and erase some of my scribbling here. Throwing in the 41.2, I'm going to get 41.2 times 1.5, that's 60. 41.2 plus 61.8 plus 7 plus 10 is 17. Does that equal 120? Remember, I can't go longer than 120. I could go 120. All right, 41.2 plus 61.8 plus 17 is indeed 120. And therefore, my maximum length of bungee is 41.2 feet. Okay, one of the formulas that we like to show is relevant to you is the Fahrenheit and Celsius conversion formula, and that is Fahrenheit equals 9/5 Celsius plus 32. And it's unfortunate that the US is still kind of stuck on Fahrenheit. If we moved to Celsius, we'd never have to learn this, but US is stubborn, so we hold on to Fahrenheit. We want to know if it is 86 degrees Fahrenheit, what is that temperature in Celsius? The nice thing about having a particular formula and I am given a temperature, I just have to plug that into the Fahrenheit position. So F equals 86. So if F equals 86, I get 86 is 9/5 times C plus 32, and I just need to solve for C. Minus 32 to both sides. I get 54 equals 9/5 centigrade. Because it's a fraction, if I multiply both sides by the reciprocal, I'll get rid of that value in front of the C. So multiplying both sides by 5/9. 9 goes into 54 6 times? Is that right? Yeah, 6 times. And 5 times 6 is 30. So if it is 86 degrees Fahrenheit, that converts to 30 degrees Celsius. The last thing I want to show you in this lecture is how to solve for a specific variable. I am not solving for a value like I did before, where I plugged in 86 for F and got a 30 for C. I'm actually going to solve this formula to where C is all by itself on one side and everything else is on the other. So first things first, if I want to solve for C, that means everything else on that side has to go away. I have to be very careful to think about what's happening to the side versus what's happening to the variable. The things that are happening to the whole entire side go first. For example, plus 32 is happening to the whole entire side, not just the c, versus the 9/5 is happening just to the c. So I have to get rid of the things that are going to the whole entire side first, and then I can deal with the things that are happening to the c itself. All right, so I need to get rid of this positive 32 by saying subtract 32. I get Fahrenheit minus 32 equals 9/5 C. Now I want to get rid of this 9/5. To do that, multiply by the reciprocal. And what I do to one side, I have to multiply to the whole entire other side. The 9/5 does go away, and I am left with C, and I'm just going to flip it around because it's easier to read, equals 5/9 times Fahrenheit minus 32. Now always think about what's happening to the whole entire side. Move that first, or undo that first, and then focus what's happening to the variable. Let's try another problem. We have S equals 2LW plus 2LH plus 2WH, and we want to solve this for H. Now, we've got to find the H first because this is kind of long and lengthy. So I'm just going to highlight my H, and I have a couple of H's. That means anything that's touching the H, I have to wait until the end to deal with it. At least that's how I cope with it. So the one thing that's not touching the H but is touching the whole entire side is this 2LW. So I can get rid of this 2LW and not touch the H yet. So let's go ahead and do that. Minus 2LW minus 2LW. I get S minus 2LW equals 2LH plus 2WH. Now the good news is the left-hand side is factorable. I can factor out this common H. So I'm going to factor that out. S minus 2LW equals H times 2L plus 2W. Okay. Now think about what's happening to the whole entire H. This whole entire H is being multiplied by this block of stuff. And therefore, if I undo that multiplication by division, divide by that block of stuff to both sides, 2W, that goes away on the right-hand side, and I'm left with only H. And that's what I wanted to solve for. So therefore, H equals S minus 2LW all over 2L plus 2W. Do not reduce it if you can't. You can't cross over this minus. You have to leave it as is. Now, you may be wondering, why in the world would I ever want to do this? Well, it could be that you're always given S, L, and W, and you're always wanting to solve for H, so it's easier to set it up with equaling H than it is to leave it with all the H's kind of all scattered around everything. Good for you. You've reached the end of this lesson on linear equations in one variable. Until next time, be seeing you.